Welcome to This Explainer. Today, we're putting on our detective hats. We're going to tackle the concepts of cumulative frequency and data spread. And we're doing it by solving a very real-world dilemma, figuring out which battery brand is actually better.
Picture this. You're standing right there in the electronics aisle. You're staring at two brands, battery A and battery B. They cost the exact same. The packaging makes the exact same big promises, but how do you know which one to actually toss in your cart? We've got to look past that flashy marketing and dive into the numbers to see how consistent they really are. It's not just about the one battery that lasted forever, right? It's about which brand you can trust every single time. All right, so here's our raw evidence. We've got the test results from 50 randomly selected batteries from each brand. They were put through the exact same conditions, grouped by how many hours they lasted, from 0 all the way to 35 hours. But honestly, looking at this is kind of a blur. You can't really tell which brand is winning just by staring at columns of numbers. We need a way better way to visualize what's going on here.
So, let's jump straight into Section 1, plotting cumulative frequency.
Okay, we're going to transform this raw data. Think about the word cumulative for a second. It literally means accumulating or building up. To find the cumulative frequency, we're just adding up the frequencies as we move down our data intervals, keeping a running total. It's an absolute game changer when you need to find the median of a big, grouped data set, or when you want to see exactly how consistent your results really are. This slide breaks down exactly how the math plays out. Let's look at type A. We start with 3 batteries that lasted between 0 and 5 hours, so our running total is just 3. Now, in the next interval, 5 to 10 hours, we had 5 batteries die. We take that 5, add it to our previous total of 3, and boom, we get 8. You just keep adding the new number to your running total. 8 plus 8 is 16. 16 plus 10 is 26, all the way down until you hit 50. And here's a pro tip. That final number, it should always match your total sample size. Now, when you go to actually graph this out, you put the duration on the x-axis and your shiny new cumulative frequency on the y-axis. But here's the absolutely crucial part, step 3. You have to plot your points at the upper boundary of each class interval, never, ever in the middle. For example, if your interval is 15 to 20 hours, you plot that point exactly at 20. Why? Because you only know for a fact that all the batteries in that group have definitively failed once you reach the very end of that time bracket.
Moving right along to Section 2, finding the median.
All right, now that our cumulative data is graphed into a nice smooth curve, we can use it to find the true average. We call this the median. It's the exact middle value of our data set. And since we're using this cumulative graph, finding it is super visual. You just find the halfway mark on your y-axis. We tested 50 batteries, right? So halfway is 25. You literally just draw a line straight across from 25 until you hit your curve, and then drop straight down to the x-axis. That number right there, that's your median duration. When we do this for both brands, it's honestly pretty close. Based on the graph, battery A has a median of about 19 hours. Battery B is setting at 18 hours. What this actually means in the real world is that exactly half of the type A batteries died by the 19-hour mark and half of type B died by 18 hours. If we just stopped here, you'd grab battery A, right? It lasts an hour longer on average. Case closed. Or so you'd think. But we can't stop there. Let's dive into Section 3, quartiles and data spread. Here's the thing. An average doesn't tell you the whole story. It doesn't tell you if some batteries died after just 2 hours, while a couple of freak ones lasted 30. To really understand reliability, we've got to measure the spread of the data. To do this, we use a percentile scale. This just splits our cumulative frequency y-axis into 100ths. We already found the 50th percentile. That's our median. But if we check the 25th percentile, the 1/4 mark, we get the lower quartile. And up at the 75th percentile, the 3/4 mark, we find the upper quartile. And these quartiles are basically a superpower. They let us calculate what's called the interquartile range, or IQR for short. Now, you might be thinking, why not just find the total range? Take the absolute highest number and subtract the lowest. Well, the total range is risky. One super dud battery or one miracle battery that just won't quit will completely mess up your data. The interquartile range fixes this. By subtracting the lower quartile from the upper quartile, it completely ignores those extreme outliers. It isolates just the middle 50% of the results, giving us an incredibly accurate measure of consistency. So when we actually calculate the IQR for our batteries, a pretty stark contrast pops up. Battery A has a massive 12-hour spread right in the middle 50% of its data. But battery B, it has an incredibly tight 6-hour spread.
the middle half of battery B's products behave almost exactly identically.
To really see what this means, let's look at Section 4, Box and Whisker Plots.
Statisticians use this super clever tool to visualize consistency, and every single box and whisker plot is built from 5 specific data points. The box itself is drawn from the lower quartile to the upper quartile, with a line somewhere inside showing the median. Then you have the whiskers. These extend out from the box to touch your absolute minimum and maximum values. And the best part? The whole thing sits right under a normal number line, making it incredibly easy to compare two things at a glance.
Now, there's just one little detail to keep in mind here. Remember how our battery data was grouped? Like the lowest category was 0 to 5 hours? Because of that, we don't actually know if the absolute worst battery died at 1 minute or at 4 hours. So we just assume the absolute minimum is the bottom of that group, which is 0. Same goes for the maximum. Our highest group was 30 to 35 hours, so we just use 35 as our absolute maximum for that top whisker. All right, looking at these plots side by side finally reveals the real story behind our data. Focus on those central rectangular boxes. That's our middle 50%, our interquartile range. Yes, battery A's median line is a little bit higher up the scale, but look at how wildly stretched out its box is. It's all over the place. Battery B has a slightly lower median, but its box is totally compact. That tiny tight box is visual proof that its core performance is just way more consistent. And that brings us to the ultimate conclusion. If these manufacturers were being totally honest, here's how they'd actually advertise. Type A? Sure, on average, it's the longer-lasting battery. If you get lucky, you'll get a great one. But Type B is, without a shadow of a doubt, the more reliable battery. With Type B, you know exactly what you're going to get. So armed with cumulative frequency, interquartile ranges, and box and whisker plots, you're not just guessing anymore. You can actually see the story the numbers are telling. I want to leave you with one final question to chew on. If you're buying a battery for your TV remote, yeah, maybe you roll the dice on battery A. But if you are putting it in your house's smoke detector, which battery are you actually going to spend your money on? Thanks for joining me for this explainer. And remember, always keep questioning the data.